right, so we got about 1 minute left before the class starts. Um, and I forgot to change the name of the live stream, so it still has the date of yesterday. But I assure you, I am not repeating the exact same material as yesterday. And I still need to make a new text channel for today, and let me do that. Uh-huh. There we go. The link to the live stream is really not necessary because if you go to my channel, you can find it over there. There we go. In other words, I am enabling people not to go find their own resources. For that, I apologize. All right, it is time to get the class started. So what we'll do today is to continue what we talked about yesterday, which is the linked list program. We do have a new lab today. It is called Structures and Pointers, which also means what we have started last in the previous class yesterday, and what we'll be talking about today are very relevant to this lab and also its code submission. So I'll talk about the timing of those in just a little bit. And right now, let's go back to the program that we were talking about yesterday. All right, so the terminal has not been touched since yesterday. I've been using the rest of my desktop, but not this portion. So this portion remained as is, since yesterday. There we go. All right, so we're going to go back and take a look at list.c, which is the C version of the code, and the TTP ASM version has not existed yet. So we'll be working on that today. All right, so we got some questions. Does anyone else just see the YouTube screen? We are seeing your YouTube screen. All right, so let me see what it is capturing. Oh, right, because I was capturing the live stream screen. So there we go. Go live. There we go. So that should fix that problem. Thank you, Eric. Okay. All right. Cool. So this should fix that problem. Okay, just from the lack of comments in the text channel, I'm assuming this is working. All right, so I am hoping that all of you had a chance to take a look at the C program and understand how it works, because that's going to be what we'll be doing today, is to turn this into assembly code. And without an understanding of the C code, it would be impossible to write and debug the assembly code. I'm not seeing any text in the text channel, so apparently there are no questions regarding the C code. If I'm wrong, let me know. So with that assumption, I'm going to move ahead and write the assembly code on the right hand side. All right, so first thing first, we have to define node. So node has only two members in this case. It has V as a member, and it is the first member of the structure. So it's going to have an offset of 0 from the beginning of the structure. And then the second one, node underscore n, is the second one. It is right after member V. So this is going to be the offset to member V plus 1. And the 1 has to do with the size of member V itself. And now we need to look at the size of a node. That would be the offset to the last member of a node plus the size of the last member. In this case, because we have an 8-bit processor, so even the addresses are 8-bit wide. So that's why we're only adding 1 byte to deal with the pointer to a struct node. All right, so now we can move on to the global variables. So we talked about global variables before, regarding how they are defined. And defining a structure as a global variable that is initialized is no different. So we have a label C, and then under C we have byte 25. Oops, typo. Byte 25, because 25 is the value of member V, and it is the first byte of a node. And then the second byte is going to just be byte 0 because it's a null pointer. So that defines C as a global variable of the type struct node, and this is how we do it in assembly. So you can probably imagine B is going to be very similar. We have 14 instead. So now the question is, what about the address of C? Well, there's no such thing as ampersand in assembly because you can see how the assembler, the syntax highlighter does not like it. So the idea is the label, the value of the label, the definition of the label C is already the address of the global variable C. So all we need is just byte C to refer to label C, which is the address of the byte that has the content of in decimal 25. So now we get down to A. Same thing, byte 65, and then byte B. There we go. All right, so right here, okay, I'm going to pause and go like, how do we know that tech is speaking of the truth, especially about byte C? It contains the address of this byte, that is initialized to 25, and then byte B has the address of this byte that has the content of 14 in decimal. So well, this is why the assembler is helpful, because we can just go through the assembler and see how this program is assembled at this point. Because it is not a good idea to make assumption and go like, let's assume this is working, and then based on this assumption, let's work on the rest of the program. That is just not a very good idea. So what we'll do now is to get out of the editor. Okay. Now I can open up another terminal. Oh, I just did that. Okay. So I'm going to open up a new terminal, so I can use one to stay in the editor and the other one to stay in the folder where I can run the script to assemble the program. And this is reverse spider, and we are submitting list.ttpasm. And then go back to this one to go back to look at the code. So this way I don't have to exit the editor, go back in, and so on. All right. So something went wrong. The assembler failed. Alright, so let's go to the assembler and find out why it failed. So we go to the source. Any type of error should be reported here. And we have a problem because I did not define the label main. Alright, that's my bad. That is indeed my bad. Alright, so now we go back here and go to the assembly side and just say main colon, and at this point we don't really need to run main. We'll just put a halt instruction here. So when this program does run, it just executes the no up, and then it will jump to main, and then it will halt immediately. So let's check it out. Oh right, I have to use the other tab in the terminal to resubmit the code. Looks like this time is good. Object code is good. Starting simulator. Okay, so we are not really interested in how this program runs because we already know it doesn't do a single thing, but we are interested in seeing how it assembles. So in the assemble tab, and scroll all the way up. There we go. So we can see how we have two bytes here. One is 19 and the other one is 00. That is how we define the global variable C. In the case of B, when we need to refer to the address of C, it puts a byte of 03 here. But that is correct because the location, the address of the first byte of C as a global variable, as a structure, is indeed 03 in hexadecimal. Likewise, when we need to refer to the address of B, the assembler gave us a byte with 05 in it. And that is also correct because 05 is indeed the address of the byte, the first byte of the structure that is our global variable b. So far so good. Okay, and this is how you probably want to write your programs. The one that is due on Monday, and also the other one, because this is how you can write your code, verify what your understanding of what the code is doing, and then once you verify the program is working up to that point, then you can proceed, write some more code. But if you cannot verify that the program is doing what you think the program should be doing, then maybe it's time to kind of pause and fix the program before going any further. Um, if you are new to this, and I think all of you are new to this, I would not write any more than 10 lines of code at the most before you test it. You can always say, but my subroutine is not done yet. Okay, how can I test a subroutine that is not done? Oh, it's okay. Just put a halt instruction, at the point where you think it should work up to this point. Because when you run the program like that, you can always rely on the trace analyzer to basically give you an idea of how your program changes the registers, how it accesses memory. Most importantly, how does it use the stack? So as long as you can use the trace and verify that your program is indeed doing everything correctly up to the point where you put a halt instruction, that's good. Okay, and that makes it possible to make an assumption and go like, okay, I know this program works up to this point. I have blah 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 in this register, blah blah blah, so now I'm going to use it in this way. Because if you make an assumption that a certain register has a particular value but you don't check, you're not sure, then when your program crashes, you really don't know which part of the program is causing the program to crash. So, so that's just a little bit of me sharing my experience with writing and debugging programs in general. Once again, you don't have to listen to it. You can do whatever you want. All right. So back to the program. There we go. So now we can start to write some code in main. Main has one local variable, which is p. So we're going to define p main p colon 0 because it is the only local variable in this case. So the 0 is referring to it would be at an offset of 0 from where the stack pointer points to after we adjust the stack to allocate space for that local variable p. So when we get into main, the first thing we need to do is to initialize the stack pointer. Okay, subdd would do that. And then the next thing we need to do is to decrement d to allocate the space for our local variable p. And as I said in the class, whenever I allocate, I automatically put in the code to deallocate. So this way, I won't forget later on. Of course, in your case, you might want to also write down some comments next to decrement d and increment d, so just so that you can remind yourself what those increment and decrements are for. Because without comments, you might be looking at your program later in the day and not really remember what those instructions are for. All right, so now we are in the subroutine, which means we can actually utilize this label. So we want to compute the address of A as a global variable and put it into P, which is a local variable. All right, first thing first, let's deal with the right-hand side first. So we're going to put the label A into register A. So you might look at this and go like, but how can the assembler figure out which one is which one? Well, the assembler knows because the first operand is supposed to be a register, whereas the second operand is supposed to be an expression that resolves to an integer. So it knows that in the second expression, A is referring to label A and not register A. So that's it. Okay, so now register A has the address of global variable A because it is a global variable. The location of global variables, the locations of sorry, I misspoke. The location of global variables are static. once it is determined at assemble time, it stays there. It is not relative to where the stack pointer points to. All right, so now we have to compute the address of P so that we can store to local variable P, which is itself a pointer. So to do that, we have to use the trick that we have been using already quite a bit. So we put the offset into register B, add BD, so that B is now the address of local variable P of main, and then we do STBA. So now we store the value of the right hand side, which is already in register A, into where register B is pointing to. So that should do that finishes this particular operation. Next, we have a loop. Okay, so whenever I have a loop, I'm going to put out the control structure first. So we're going to say this is the while loop in main, and this is the beginning of that loop. And I will automatically put in while end, because the loop has to end at some point, and right before the end, it has an unconditional branch to while begin, because that's how you perform a while loop. So now I have to specify the condition, evaluate the condition, so that I can determine when I can get out of the loop. So we have to evaluate P, and we have just put a value into P, but I'm not going to count on that. So I'm going to recompute the address of P and then get to the value of P over here. So it's going to be a little bit boring because it's kind of the same code over and over again. We have the address, but this time we want to load B into B. So now register B has the value of P. Now we can compare that to 0, because when we use a construct like this, it is really just comparing and asking, is P different from 0? That is what it's asking. So we can use JZI. JZI is branching if and only if P is indeed 0. Oh, I forgot one thing. Forgot the AND BB. Because if I don't have the AND BB, it's not going to get through the ALU, and therefore it's not going to influence the Z flag. So I have to use AND BB in order to force it through the ALU. Now we can use JZI to branch if and only if B, which now has the value of P, is 0. So JZI to main while end, because if P is non-zero, we want to stay in the loop. So when it is 0, we want to get out of the loop. So the body of the loop is now between the JZI and the JMPI. So we don't have printf in assembly language. So in order to simulate what printf would do, I'm going to do this trick here. So what I'm doing is I am going to put I'm going to use an underscore to begin the name of this global variable, just to emphasize that it is not, there's no equivalence of this in the C code. I'll just call this output, which is really just a single byte. So whenever I want to output something, I'm going to put that byte into this byte over here, which is defined by the label underscore output. So that is how I'm going to do a very crude way of printf unsigned P points to V, because the idea is not to implement printf, which is actually fairly complicated. The idea is, how do I get to member V of the structure that P points to? So once again, that is the notation. That's the meaning of the notation that looks like a right arrow. Looks like we do need to get to P again. So what I'm going to do now is to kind of be lazy, and I'll just go like, okay, B has the value of P already, so I'm not going to go through this code here to put it into a register. So having that piece of information here, we know register B, the value of register B is the address of the first byte of a struct node. So we know that already, and we just need to access member V at this point. So all it takes in this case is to load LDI load immediate, the offset to member V, which is represented by node underscore V. Oh, I have designated a register first. Register A is fine. Node V, which is the offset to member V from the beginning of a struct node. And some of you may be saying, but that's just 0. Why don't we just put a 0 here? Well, I'll explain why in just a little bit. All right, so then we need to add that to whatever B has, because B has the address at the beginning of the entire structure. A has the offset from the beginning of the structure to the member that we want to access. So by adding A to B, B is now the address of the member that we want to access. But it only has the address. So we don't want the address, we want the actual content. We want to know what it is. So we'll go ahead. Okay, I am looking at this code and go like, okay, I'm going to do it this way first, and then I'm going to go back and optimize it a little bit, okay? So we'll just keep going in this direction. And then we'll do LDBB, so that now register B has the value of member V of the structure that P is pointing to. And it is time to put it into underscore output. So now we need an LDI and then pick another register. Yeah, I don't have enough registers to, well, okay, I'll show you some techniques here. So we'll load LDIC and then underscore output. So so register C now has the address of the byte that I'm going to use for quote unquote outputting something. And then we do a SDCA, oh, B, sorry, that will store the value of member V of the structure that P is pointing to the global variable that is called underscore output. So that's kind of how I would emulate the printf statement to quote unquote output something. So the next statement looks kind of interesting because we are using P on both sides of the assignment. Well, don't let that bother you because we evaluate the right hand side first and then we evaluate the left hand side. So we are not pulling the rug from underneath ourselves because we're going to use the existing value of P to compute the right hand side, and then we're going to change the value of P after that. So it is not cyclic in any nature by itself, even though it's inside the loop. All right, so when you look at this code, you go like, we have to get back to P. Well, we had that earlier, right? So we had that earlier until we performed this add BA instruction that kind of screwed things up a little bit. I wonder if there is a way to save the value of register B at this point before the add instruction, so I can use it later. So I don't have to go through all the initialization, getting from the offset, adding it to the stack pointer and stuff like that. Now there are two questions here. One is, can I do it? And number two is it worth the trouble to do it? Well, we won't know what the answer is until we actually do it. So we're going to do it now. So the idea is the stack is really quite useful because what we can do here is we can just push the value of B on the stack and then pop it later on, so we can reuse the old value of B before the add instruction. So to do that is pretty easy. Decrement D, stdb. That's it, right? So we push the value of B on the stack, and then when we need it back, we just go here and go like, okay, give me back what I just pushed earlier. So we have an LDBD and increment D. So this is a pretty popular way in assembly language programming in order to save the value of a register so that we can use it later on. But when you compare this approach, which uses up 4 instructions, of the 4 instructions, 2 require the access of memory because ST and LD, they both access memory, which means in reality they are slower instructions in real processors. So it is clean in a way, in the sense that it is pushing and it's popping. It's a very cool trick to do, but it's not saving us any time, because in the other using the other approach, which is to recompute the address of P, it doesn't take much. Okay, all it takes is LDIB and then underscore P, a main underscore P, add BD. That's it. That way we computed the address. So from the address, we are going to first. That's it. I mean, so these two instructions is doing the job of these four instructions, pushing and popping. So that means, pushing and popping really is not worth the trouble, okay, in this case, because recomputing the address of P is easy, okay. It's not taking much time. All right, so now we do have a little bit of an optimization question because we need P on the right hand side in order to get to member N of the structure that P is pointing to. But we also need P, or the address of P, on the other side because we need to store back into that location. So the question is, how do we optimize this code so that we can use the least number of instructions? So this is how I'm going to do it. So we'll LDI A again with the offset to member N, and that would be node underscore N. But this time, instead of adding B to A, I'll reverse the order. I'm going to add B to A. So B is still having the address of P, but at the same time, register A now contains the address of member N of the structure that P is pointing to, which is only one step away from computing the entire the value of the right hand side. Because the value of the right hand side is not asking about the address of member N of the structure that P is pointing to, it is asking about the value of member N of the structure that P is pointing to. So that means I need an LDAA in order to get to the value. So now register A has the value of member N of the structure that P is pointing to. Where do I need to store it? I need to store it back into P, which means I need to get to the address of P, but that is still in register B. So STBA will now get the job done because register B still has the value of the address of local variable P, because once I calculated that, I never destroyed it. I kept it around. I used the other register, register A, to compute the address of the of member N, and then later on I also use register A to get to the value of member N. So that should do it, and I'm not worried about, what about the loop, what about the control structure. That's all done already. All right, so I think this is it. Okay, yeah, I think this should implement what is equivalent to the C code on the right hand side, on the left hand side. So it's time to test the program. So let's go ahead and resubmit this particular assembly language program. I had to change the uh-oh, looks like we might be stuck in an infinite loop here. All right, well, oh, maybe not. Now it's doing the simulation. Now, in case you suspect it is stuck in an infinite loop, you can use Control C to stop the script, like this. I am thinking about, putting a timeout in the script so that way it will stop after like a certain number of seconds. So let me just do that. I can re-upload this script later on just so that you guys can get the code that includes the timeout. All right, so so this is the code to run the simulator, and in Linux and also in Unix, timeout, and then you specify the number of seconds, let's say 15 seconds. That will basically run whatever command is right after that for up to 15 seconds, and then at the end of the 15 seconds, it will automatically time out, kill the program that doesn't exit after 15 seconds, and continue with the script. So we're gonna make that change. And in a way, if this program has an infinite loop, which means it's not doing what it's supposed to, it's actually a good thing because I can then illustrate, how to debug a program that is like this. You're stuck in a loop. We have no idea, just by staring at the source code, why it is stuck in an infinite loop. So now we give it like 15 seconds. After 15 seconds, it's going to stop the simulator and submit the trace regardless. It's going to be a huge trace too. So it might take a little bit of time, for the spreadsheet to analyze it. All right. So now we go back to the trace analyzer. And the first thing we do is we're going to go check how many lines or how many rows are in this particular trace. 6,906 lines. Okay, that tells me that we are probably stuck in a loop. Now is the fun part. The fun part is now that we know the program is not working, what are we going to do? I used to be a TA when I was a grad student over at UC Davis. And even at UC Davis, I observed people who were in a hurry to get their programs done. And when the programs do not work, guess what they did? They make random changes to the program. They would change less than to less than or equal to, comparing to the boundary condition, and then try to compare to the boundary condition plus one, that sort of stuff, which is very, very illogical, because that actually will only make it worse. Anyway, we are going to find out whether we are still in the loop. So to find out whether we are still in the loop, we go to the Assemble tab, and then we look up the label representing the beginning of the loop, which is while begin. This is the while begin, and it is at location 1, 2. So when we get back to analysis, what we are doing is we are trying to find out whether 1, 2 is repeating, and it should repeat, but only up to there should be 4 occurrences of 1, 2, and then after that we should be all done. All right, so what we'll do is we're gonna do a Control H, which starts the search, and then we are looking for, in this particular column, 1, 2. It's already limited to this range, and we'll now go find. Okay, that's our first iteration, second iteration, third iteration, fourth iteration, fifth iteration, and so on. So we did end up with a loop. We are now performing more iterations than we should. All right, well, but it should have stopped, right? So why is it not stopping? So we can either go to the source code and reason it out, or we can go to the trace to basically compare what we think the program should be doing versus what it really was doing. So which way do you guys want me to do? You guys get to vote. Okay, so I got some people saying analysis, and I'm assuming that is the analysis of the trace. And we got one person saying source, so I'm going to do both. So it's not exactly a vote. It's just me collecting opinions from the class. All right, since I'm already in the trace, we'll go for the trace analysis approach first. So in the trace analysis, we first put we want to first compute the address of we want to compute the address of of the of p, and then get to the value of p. So the first thing we did was to change b to 0, 0, which is the offset, and then we add d to b, and it is at location F9. That tells me that something is not right, okay? Because it really should not be at F9, because it should be at FF. So right away I go like, the stack pointer is not pointing to the place where it's supposed to, because the stack pointer is supposed to be pointing at location FF, not F9. So that means, I need to use the trace to go back to when was the last time, D got changed. So D got changed here on at location 1B in the program. So I go to the Assemble tab, go to location 1B, and we have decrement D over here, which is a leftover of the approach that I used earlier, I think. Let me think about it. Yeah, it's a leftover. I forgot to remove that line. So that is why the program is not working, because I decided not to do the push pop approach. I removed some of the instructions related to the push and pop, but I did not remove all of them. So that is why the program did not work. So this is a combination of analyzing the trace to find out that, hey, this doesn't look right, and going into the source code to figure out why the stack pointer got changed when it is not supposed to. So it's a combination of the two. I hope this satisfies the requests, both of the requests, in terms of analyzing the trace and also analyzing the source code, because it's a combination of the two. So now we go back to the source code, okay, and look at the program and go like, tag, you need to be more careful because we decided not to do the push and pop approach. So that means this really should not be here. And I think I removed the wrong instructions. That's also bad because I forgot to I removed the wrong instruction basically. So we still need an add instruction here to register B from A. That way we get to the address of the member V, and then we get to the value of member V, and then we output that to underscore output. So that looks right to me. And now I'm super cautious about, did I remove the pop entirely from this code? And the answer is yes. The pop is entirely gone. All right, so save the program and we'll run it again. This time I don't think we'll be stuck in an infinite loop anymore. So if you have any questions regarding the debugging process, how I figure out what was wrong with the program, you can go ahead and ask those questions. I think that is actually more important, well, at least as important as the actual knowledge being taught that's specific to assembly language programming. Because the technique of debugging a program can be translated to other languages too. All right, so let's take a look at the analysis. All right, this time is a whole lot shorter. All right, cool. And how do we know whether the program worked or not? Okay, that's our next question. So the way we can check whether the program worked or not is to see what values have been written to the location known as underscore output. So in the Assemble tab, we look up the location of that label. So underscore output is right here. It is at location 09. And then in the trace, now we can focus on column C, because column C reports overwriting memory locations. Now you can just do a visual scan like, oh, I find one right to location 09 here. You can do that. But you can also make it more systematic. You can type Control H, pop up the find and replace. And this time we are going to specify something like this. Now this is regular expression. You don't have to learn. I don't have to use regular expression in this case, so I'm not going to do it. So we are looking for something that starts with asterisk 09, which stands for dereferencing location 09, and then the single equal symbol. So we'll just specify this as what we are searching for, and then we can now click find. So we find 41. 41 is the 65, and then we go back to the beginning, hopefully. Oh, okay, so we only see one of them, which is also incorrect, okay, because we're supposed to be seeing 3 of those numbers. All right, so the program is still not working because in the C code it printed out three different values. Okay, so we want to now look at the source code to find out which structure has which code. So we go to the Assemble tab. A has the for one, so it never got to B nor C. Okay, so after A, it it probably exited the loop. So in the analysis, we want to see we want to confirm that, and we can see that we got to the halt instruction at 2B right here, and we are matching the address of the halt instruction at 2B. So the program basically exited early this time. Instead of getting stuck in an infinite loop, it exited early. So now the question is, how did it exit it early? It exited early because I can see right here we overwrote the location of local variable p with 0, 0. So now the question is, how did it get that 0, 0? In other words, I'm executing the program backwards now. It is only possible because we have a trace. So register A, got the value of 0, 0, and that is what we put into local variable p, and that's why it terminated the loop. So now the question is, how do we get this, how do we get AA into, how do we get 0, 0 into register A? Okay, that's the next question. So this is the change at location 25. So we go to the Assemble tab, we get back to location 25, and that's our add AB, add BA, add AB, sorry, is adding B to A. And that looks wrong to me because after this, register A should not be a 0, 0 because we're supposed to have the address of member N of the structure that P is pointing to. So now we go back to the analysis and ask, how did it go wrong? So we can see B is here. Oh, okay, I can see it. So B is the address of P, but we never dereferenced it. Because okay, if I go back to the Assemble tab, we put this here, we got to the address of P, but we are not really interested, we should not be interested in the address of P, we're interested in the value of P. Because P itself is a pointer, and we want to know what it is pointing to, we are not interested in where P itself is located at. So right after this add BD instruction, there should be a LDBB instruction because we want to get to the value of P because we are interested in what P is pointing to and not where P is located at. Alright, so we go back to the source code and we'll fix that. So the problem is right here. I forgot about a LDBB. And this is what happens when I don't comment my own code. Because when I don't comment my own code, if I had commented this code, I would have written here that B now has the address of P, and then I would realize that I'm adding the offset to the wrong thing. But instead, I chose not to write down the comments. So as a result, this is the consequence of not writing down comments as I write code in assembly. Alright, but the end result of this consequence is actually great, okay, because I made several bugs in this program, and I can now illustrate to you how to debug a program. Now, if this class says, if people in this class are now thinking, go like, Tech, I spotted that error long ago, long before you debugged your own program, and I got the techniques down for debugging. Well, I will be very glad to hear that because debugging is one of the few things that are very difficult to teach. All right. So the program is stuck in an infinite loop again. And when it does exit, we'll find out why it is stuck in an infinite loop. All right, so now we go back to analysis, and if we go to summary, we should find, yep, 9,333 rows. That's a very strong indication that we were stuck in a loop, infinite loop, unintentionally. All right, so we would like to find, all the updates to underscore output. So first of all, we locate underscore output. It should still be at the same place as before, but I want to make sure. So underscore output is at location 09. And when we get to analysis, we are overwriting location 07. So location 09 FF is 07. That is correct. This is the initialization of the pointer P. It should be pointing to A as the global variable, which is at location 07. So that part is correct. And then we overwrote output underscore output to 41, which is the 65, and that is correct as well. This is questionable. Okay, why are we changing the first member to why are we changing member V of the structure that we know as global variable A to 05? So this is highly suspicious at location 28. So we go back to location 28. Location 28 is right here. And this store is supposed to store back to P. So it's not supposed to overwrite A, it is supposed to overwrite P. Which means okay, I see why. Because B is now the value of P, not the address of P anymore. And this particular code down here is relying on the fact that register B has the address of P, but instead it had the value of P already. Okay, so let's go ahead and fix that bug. There are several ways to fix this bug. One quick and easy way is just to use a different register in this case. So we'll put the value of P into register C so that we can add C to A in this case. So this way we are preserving register B to contain the address of P. So all of this stuff here is because I was trying to optimize the code and not to reload, a register with the offset and then add that offset to register D. And you can probably kind of understand now why, when you are writing your code, you may not want to, shoot for optimization, because optimization means in your head you're going to have to track which register has what. And given that I am not writing down any comments to remind myself which register has what, this is what happens. This is the consequence of not commenting my code and just relying on my brain to keep track of all of that stuff. And you might say, but Tech, there's only three things. There are only three registers being used here. Yeah, well, I do have a really faulty short-term memory, so it doesn't work that well. But as I said, this is great because it's just a great chance for me to illustrate how to debug a program. Yeah, I kept saying that to cover my tracks, right? Because Tech, you made stupid bugs in your own program, and now you're trying to cover your track and say that, yeah, this is great because I get to demonstrate how to debug my program. That's one way to look at it. All right, so this time the program is working. So the first output is 41, which is our 65. The second output is 0E, which is our 14. And then the third output is 19, which is 25. So that should be the exact output of the C code. I still have the C code around, so we can go ahead and just run the C code too. So the C code is in /temp L list. And those are the three values to be printed in C code. So the assembly code is now doing exactly what the C code is doing. All right, so I'm going to pause a little bit and see if you guys have any questions. And I'm going to go back to the editor here just so that you can look at the code both in C and in assembly and see if you have any questions about the translation of the code. Alrighty, I'm not seeing any questions. Um, was that okay? I mean, did you guys understand the debugging process? I mean, you can also always watch this again, to kind of understand, what bug I introduced the program to begin with and how I noticed what went wrong with the program by using the trace. And one thing that is really good about the trace is it allows you to execute a program backwards because it shows the effect of every single opcode in your program. And as a result, you can now execute your program backwards and find out how you got a strange value at a certain location by just kind of tracing it backwards. That is a tool that is not going to be available when you're writing programs in general in C, C++, or Java. All right, Paul is typing something, so I'm gonna wait a little bit. All right. So, is there a use case or particular problem that linked list would solve? Ah, okay, that's a very interesting question. If anyone in this class has taken CISP 430, which I would not be surprised because CISP 430 can be taken, before CISP 310. CISP 310 only depends on 360. So I'm gonna take a look here. Okay, so linked list application. So just do a Google search on linked list application, and you will find, the it's basically a data structure in CISP 430. It allows you to create a construct that has a variable length, and it can go on and on and on. And the best part is what each node is, what each location, or what each link of the list is representing can be a huge structure itself. So it gives you all kinds of flexibility in terms of, as long as you have something that is sequential that you want to represent, a linked list can do it. It's better than an array because an array, especially in C and C++, once you allocate an array, the length of the array is fixed. You cannot change the length of an array once it is allocated. And I don't really care how you allocate it. It can be static, like in the case of a global variable. It can be auto, which means it is on the stack. It can also be dynamically allocated. But once an array is allocated in C or C++, you cannot make it longer. You can always use less. Okay, you can only use the first portion of an array, that's fine, but you cannot make it any longer. By using a linked list, you can now just keep attaching additional nodes to the end of a linked list, and then you can make it longer and longer and longer. So that's one application of a linked list. The other application of a linked list is a little bit more involved because you can use a linked list to also implement LIFO, last in, first out. And if you keep track of two different pointers, one pointing to the beginning and one pointing to the end, you can also use a linked list to implement a queue, which is first in, first out. So a linked list, a singly linked list, which means we only have one, the arrow only goes in one way. A singly linked list has a lot of application in computer science in general, and that is also why it is probably one of the first data structure to explore in CISP 430. All right. Um, that's a very interesting question. The answer is yes and no. Okay. Um, so disk storage, as you might imagine, okay, your disk is like a huge array of sectors. Okay, one sector has typically 512 bytes. Um, at least in terms of the hardware. Okay, in terms of software, sometimes we cluster them and go, okay, we have a unit of 4K. Okay, so when you create a file, it is allocating 512 bytes at a time or 4K byte at a time. So when you run out of that particular block, then you have to allocate an additional block somewhere on your hard drive and some sector and link those things together. So in certain file systems, I think in FAT, okay, file allocation table, this is how it is done. Every they call it a cluster. So every cluster contains a pointer pointing to where the next cluster is, which is problematic because now if you have a huge file and you want to find where you can find the sector corresponding to like in the middle of the entire file, you have to linearly track through all of those pointers until you get to the cluster that you want to access. So it's not very efficient. Okay, it gets the job done, it's just not very efficient. So FAT32, FAT32, which stands for File Allocation Table 32, which was used in DOS and also earlier versions of Windows, rely on something like this, which is a linear list in order to keep track of where the segments called a cluster, where each cluster is in a file. In more advanced file systems such as NTFS, extension 3 of Linux, and so on, instead of using a linked list, they use a tree structure to do it. So a tree structure allows you to very quickly locate, where a particular cluster is, because the depth of a tree is only log of the number of entries that you need as a part of the tree. So all of these terms can sound really foreign to most of you because you have not taken CISP 430. So I'm not sure whether the answer is making any sense or not. But that should answer Paul's question. All right, so let me take a look at the time. It's only 6:30. Wow. So I am going to go into the lab for tonight and also the associated programming assignment a little bit. And also I'll make some recommendation of how to approach the Fibonacci program. So maybe I'll start with the Fibonacci program first. All right. All right. So once again, I want to remind the class this question will give you some idea of how to write the code for the Fibonacci program. This is question number 6 of the lab that is called params and return value. So you might want to look at that. Okay, so that's one. And then I'm just looking in the text channel in Discord. I believe it is the 20th. So if you look up July 20th, at the end of that text channel is recursion.zip. So in recursion.zip, I also illustrated a program that is recursive, but it's only recursive with one point of recursion. Fibonacci has 2 points of recursion. So let me go back to the Fibonacci program, and I'll just make some recommendation of how to write this program step by step, or in what order to write this code. So let me see if this has the C code. And I definitely do not recommend oh, okay. So I think the code is in question number 3, the C code. Yeah, there we go. So when you look at this code, it's like super easy, right? Okay, so I'm gonna copy and paste it into my text terminal and take a closer look at it. Alright, so when you look at this code, it looks kind of easy, but I would probably, just write this code in steps, okay? So the first program that I will write is just that. You go like, but that's not even close to writing the actual logic of, the subroutine. You're right, because I want the program to stop right at the entry point, just so that I can confirm what is on the stack and what the stack pointer, where the stack pointer is pointing to. So that is the first step. That really is just the first step. Okay. The second thing I would do is to access n. Okay, so you would insert some code here to basically get the value of n into a register. Okay, I don't care which register. It can be A, can be B, can be C. Just get it. Okay, just get the value of parameter n into a register and then halt and verify that you can indeed get the parameter into a register. Once you can do this, I'm just going to return it. Okay, so we'll just go ahead and then we just return n itself. Okay, don't return anything else, just return n itself. Don't even compare, just return it. Okay, because if you can get this done, okay, and you can verify that this is done correctly in main, because you will be storing whatever the parameter is back into the local variable that belongs to main. So if you can do all of this, then you know for sure that you understand how to return a value, and also you know how to get to the value of a parameter. So once you're done with this, I would do the compare, okay, but only implement one branch, the non-recursive side, which means you're so basically the other branch, the branch where it contains recursion, just give it some random value, okay, give it 123, okay, so that you can differentiate the cases of, okay, what if n is less than 2? If n is less than 2, does it return just n itself? If n is not less than 2, does it return the constant of 123? So that you can tell whether your conditional statement or the ternary expression is implemented correctly or not. Now, if you can confirm that, then I would go here and start to look at the recursive call and approach the recursive call itself. So in other words, do it really, really step by step. Okay, because if you try to write 60 lines of code and try to run the program hoping that it's going to work, I can almost guarantee you that it's not going to go. It's not going to work, and you will have like 60 lines of code to figure out. Okay, but where is the error? Okay, where's the first line that went wrong? So by writing this code, like step by step, it seems like you're wasting your time because you're making very small steps. Like every 5 lines, 10 lines of code, you basically debug the program again. In the long run, it's going to save you time. So that's my recommendation of how to get started with the Fibonacci program. And then we are going to move on to the lab for today. And I might as well release it now. So the lab for today is structures and pointers, which we have just talked about since yesterday. Since I think mid-class yesterday, we have been talking about structures and pointers. All right, so let me get it released. Today is July 22nd. Okay, let me double check. Yep, 8:20 p.m. There are not really a whole lot of questions in the lab portion. Most of the work is going to be the actual coding, and there's no passcode in this case. And I'm going to let you guys see the correct answer after the end of the lab. So we'll put that same time over here and save and publish. There we go. So this is pretty easy, okay? I think most of you can get this done, pretty quickly. The part where it is difficult, or it's going to be a little bit more work to do, is the code associated with this one, which is an assignment that requires a submission of a file with an extension of TTP-ASM. So the code is not shown here. It is in the lab itself. So let me go back to the lab. The last part of the lab is going to show you the C code that you need to implement in assembly code. So getting back to preview and the spacer. There we go. So this is the subroutine that you need to implement. It is called traverse. It has nested conditional statement, and it also has a pretty nasty looking statement in the middle here. So what I'm going to do is I will give you an explanation of what that statement in the middle is doing and how to look at it. So we're going to cat this to, oh, I cannot remember what name we're supposed to use here. I'm going to use list. No, that's going to overwrite my other program, which I don't want to do. Gosh, I cannot remember what name you're supposed to save it as. Probably no particular name. It is still, it's not a linked list this time. It is actually a tree, so I'm going to name it as tree.c. There we go. All right. So now that we have the C code, let's go line by line and find out whether we know how to do that or not. I think this we know how to do already, okay? Because I did something almost exactly like this in the code that I wrote today, checking whether a pointer is null or not. And somebody's going to say, but the one that you did today was using a local variable. This one is using a parameter. Well, if you set up your labels correctly as offset to those items on the stack, it would have made no differences whatsoever. And then we have to check whether a particular member of the structure pointed to by PTR is null or not. So we already have the code to access the value of a member of the structure pointed to by a pointer. So that code is also in the sample program that I wrote today, and remind me to upload that at the end of the class today. So that's done already. Now we have the passing of array and the passing of the value of a member of a structure pointed to by a parameter. This part is kind of done already. This one, I'm not sure, right? Because the array looks kind of nasty. It is a pointer to a pointer. Well, as long as it is a pointer, we are really just passing whatever was passed to me along in the recursive call. So it really is just grabbing whatever parameter was passed to me. Now remember, we're getting the value of the parameter, not the address of the parameter. And then we just pass it along, okay? Whether it's a pointer to a pointer, or a pointer to a pointer to a pointer, it doesn't make any difference, because in the end, they are all pointers. Every single pointer only uses up 1 byte in TTP-ASM. So the real nasty part is this statement here. That really is the only part that is kind of super nasty. The other part is really doing the same thing as the earlier part, except instead of referring to member L, this part here is referring to member R. So for the most part, if you can get the first part done, the second part is copy, paste, modify. So this is the part that is kind of nasty. So the question is, what does it mean when we have a post increment that is outside of a dereference? That is, I guess, the question that most people have. Because the right hand side is simple, okay? The right hand side is referring to a member of a structure that is pointed to by a pointer. If you're getting sick and tired of me saying that, that's because I've been saying it a lot. The left-hand side is the nasty one. So the question is, how do we look at the left-hand side? So the way we can look at this, and you can probably write it down or just jot down the time at this point, is you can basically look at the post increment as not here, and then as a separate statement. Okay, as a separate statement, you perform the post increment, and the post increment is the same thing as just adding 1 when you do it after the original statement. So this, I hope, is easy to read. Okay, and dereferencing again is really just dereferencing again. So the extra parentheses are no longer needed here. So we are basically just storing whatever the right hand side is to whatever is pointed to by the pointer that is pointed to by array. Let me say that again, because I'm pretty sure someone in class is already thinking, can you say that again? But don't want to ask me in the text channel. So let me say that one more time. This left-hand side is storing to a location that is pointed to by a pointer that in return is pointed to by array, which is our parameter. Okay, now exactly how you're going to implement that, I will leave it to you, because we have all the instructions that are needed in order to get this done. What about the next line? The next line is saying, let's get to array first. Find out where it is pointing to, grab the value that it is pointing to, add 1 to it. That's the right-hand side. Once we have the value of the right-hand side, we now need to determine where we're going to store it. We are going to store it to the location that is pointed to by array. That's it. So you just have to read this code, step by step, and do it one step at a time. Okay, I myself, always work on the right hand side first, work out the address of the left hand side, and then do the store. So do we have any questions about the subroutine traverse, which is something that you are going to have to implement in order to turn in the code? All right, I am not seeing any questions. So when you're writing this code, there's also an approach to do it. You basically want to make it work, check the condition first, make sure the condition checking part is working, and then just be able to do this once. Okay, don't do the recursive call, just do this once. And the way you want to approach this program is really to look at the C code, look at the behavior of the C code first, and then translate that into assembly code. I am going to show you the lab of today. Let's see, this is not, yeah, this is the one of today. All right, so let me find where the main code is, the main of the program is. This is main, but it's not the main of traverse. So maybe I forgot to give you the main code so that you can test it. All right. So I'm going to give you the code, the complete code, including the main, also, so that way the program actually runs. So let me go switch to the command line here. Second part of question 2, maybe. No, this is not the same program. This is not a tree node. Question number 3 is getting into it. So I'll give you the code, no worries. All right, so I'm gonna put it like this side by side because I need to see what I'm copying and pasting. So we have struct node, and then we have, now this is the important part, is you want to make sure that your code is not reliant on the ordering of the members. Struct node star L, struct node star R, and then we are gonna define a little tree here. Okay, so it's the same idea. We have, struct node. Um, let me see. All right, so I think 5 would do it. Okay, so we're gonna start with E, and E is gonna have, the value is not important in this case, so we'll go ahead and start with 200 here and 0, 0. So the two zeros are corresponding to L and R. They're both null pointers. And then we have struct node D. And D is going to have a value of, let's say, 100. And its left hand side is null. And its right hand side is the address of E. Then we have struct node C. And we'll make this 1. And it has 0 and 0 for both of the pointers, L and R. And then we have struct node B. And this one is going to have 2, where the left node is C, the right node is nothing. And then we have struct node A, where it has a value of 10, and its left struct node is going to be B, and its right, sorry, that's the left, and then the right one is going to be D. There we go. And then we have main. And in main, we just need to make a call to traverse. And we also need an array in order to pass the address, an array, a pointer to the array, and then we pass the pointer to the array, or the address of the pointer to the array to the subroutine. There we go. So we have, let me check the types. Uint. Okay, there we go. So got to remember to do that. And then over here we have uint 8 underscore t. I'll just call this buffer. And buffer can be big, can be small, doesn't really matter. I'll make it 10 characters long. Uint 8 underscore t. This is a pointer. And now we can call traverse. So when we call traverse, pointer needs to be initialized. So pointer needs to be initialized to the beginning of buffer. And then when we call traverse, we're going to pass the address of A as the first argument, and then we'll pass the address of PTR as the second argument. And that's it. Return 0. Alright, so this is the C code, and let me double check and make sure the C code works. Alright, so let's see. Well, it has a type checking error. Typo on second line of main. Oh, right. There we go. That's what syntax highlighting is for. Okay, very good. Thank you. So GDB tree, and I'm just going to verify the running of the program. We'll put a breakpoint on line 39, run the code, and if I print out what is in buffer, it's going to have the value that we saw earlier. So we have 1, we have 2. This is \n is 10, d is 100, lowercase d is actually our 100, and then \310 is our, what is that? 200. So that's the outcome of this code. I will give you the assembly code of main and also the initialized global variables too. So this way, you will have a platform to test your code. So I'm going to do that in the lab time, which is coming right up, so that by the end of the lab time today, when you're ready to actually jump in and write the code, you have that. Actually, it does have these initializations, but I will make one that is corresponding to what I put into the code today. So this way you have the C code and you are going to have the assembly code matching up. All right, so it is time to get your lab started. It's already there. Yeah, go ahead. I thought there was a question or a point. Somebody was using the voice channel. Okay, I have not yet decided when this is going to do. It's not going to be Monday because you might need a little bit more time, but I would definitely not sit on this one because this one will take a little bit of time to debug it. And I cannot make it too late either because next week is our last week and next Thursday is our final exam. So I need to make this due latest by Wednesday in order to give you the solution in time so that you can get used the solution of this program to help you prepare for the final exam. So the trade-off here, okay, the reason why I'm hesitating, to determine what day I want to make this due is if I make it the 28th, then you won't have a whole lot of time to look at the solution and then ask question. If I make it the 27th, you may not have enough time to get your program running to turn it in. So that's the dilemma that I'm facing. So let me put it on the 27th for now. And if I see a lot of people cannot get it done for one reason or another, then we'll go ahead and change it. But there's a price to pay to change it to the 28th because that means you won't have a whole lot of time to look at the sample code either. All right, so I'm gonna put it on the 27th. You still have plenty of time. I mean, you do have a weekend and Monday to work on this. So that's it. All right, so I'm done with the lecture, and I'm going to work on the assembly code corresponding to the C code that I just presented. So that way you have a platform to work on this particular program. So I'm going to upload the code once I'm done with the assembly code corresponding to the tree program. All right, so I'm going to